Okay, hello everyone. Thank you for joining. We'll do some introductions here, give everyone a little bit of time to join us. But welcome to our Sodick and Friends webinar series. We're happy to have the Madison Group here. Jeff Jansen will be presenting, and I am going to introduce myself. I am John McNamara, sales engineer here at Sodick Plus Tech, cover Minnesota and New England area, and been with the company for about 3 years now. So I'll give it off to Cody real quick, just so he can introduce himself.
Okay. Hello, everyone. I'm Cody Mrai. I'm sales support manager. Thank you for joining us today. My main role communicates special requests from the customers in the America to engineer in Japan and help make them a reality. I also provide a variety of the other supports. Yeah, thank you.
Thank you, Cody. You guys may notice that my name is coming up as Kohei Shinahara. I'm having some technical difficulties on my computer right now, so I'm using his, but I'll turn the screen and let Kohei introduce himself as well.
Okay, thanks for joining this webinar. I'm very happy that we having the all technical subject into our community. So enjoy the show and please give us feedback if you have any. Thank you.
Thank you, Kohei. So before we get started, I just want to explain for those of you who have joined us before, you probably know how this works, but for anyone that's new, as we're going through the presentation, there is a Q&A tab at the top. If you click there, you can submit questions throughout the presentation, and then at the end, I will go through those questions and relay them to Jeff, and Jeff can answer them. That'll be about 15 to 20 minutes at the end of the presentation. So with that said, let me introduce our speaker today. His name is Jeff Jansen. He is the Senior Managing Engineer at the Madison Group. He's a graduate of Carroll College and the Milwaukee School of Engineering. He is also a fellow of the Society of Plastics Engineers and has over 30 years of experience in the industry. He specializes in failure analysis, material selection, and lifetime prediction, and frequently discusses these topics in an educational setting like we're doing today. So without further ado, I'll hand it off to Jeff and let him give his presentation. Jeff?
Thanks a lot, John. Welcome, everyone, to today's presentation. It's going to be an overview of plastic material selection. What we're going to be talking about in the next hour or so is really just a snapshot. We could talk for a long time about material selection, but kind of an overview, kind of a flavor of the topic today. It's my goal over the next hour or so that you'll gain an appreciation of how polymer structure and plastic composition determine performance properties, and also get a better insight into that material selection process. We're going to talk about material considerations, plastic structure and composition, and then material selection. So if you were thinking the whole topic would be on material selection and that process, well, that's going to come at the end. Material selection, good material selection that avoids failure, really you need to understand a number of things about plastic materials. That's our material consideration. And then you need to understand how structure and composition affect performance. And that's what we're going to be talking a little bit about also. Again, to get some background so that, again, we can do proper material selection to avoid failure, because that's the goal here, is to avoid failure. So why are we talking about material selection? Well, I've been doing failure analysis for about 30 years, and I see the same mistakes being made over and over and over again. And one of the top reasons for plastic failure is improper material selection. I don't mean to imply by that list that it's the number one, but it certainly is in those top 6 things that I see over and over and over again that lead to failure within plastic components. And it's not selecting the right material for the application. So again, it's a very, very important topic. That's why we're talking about it today. I also did a survey where we looked at a number of failed plastic parts, and we broke them down into what are basically the 4 primary factors for plastic part performance, which are the material, the part design, the manufacturing, and then the service environment. And again, those 4 factors are going to determine how the plastic part performs. When we looked at failures, and I took this survey, material selection and quality played a role in nearly half of the failures that came up. So again, not saying again that was the primary factor, because oftentimes there are 2 or 3 factors involved in a failure, but material selection played a role in nearly half of those plastic component failures. So again, reinforcing why it's such an important topic. So material selection is an ordered process to systematically eliminate materials that are unsuitable and then qualify or identify 1 or 2 or a small number of materials which are the most suitable for that application. Again, we're going to be choosing a material that meets the performance and cosmetic goals and really all the goals. And we're going to talk about what those factors are over the product's lifetime that can be easily assembled and manufactured at an acceptable cost. Okay, so really the whole package is what we're going to be looking at. And later on, when we get to that process, you'll see how that all comes together. So failures due to poor material selection, as I've indicated, are very common. And I think that they're essentially related to a lack of awareness and understanding of polymer structure and composition and how that affects performance. Because really, when we're talking about improper material selection, we're talking about the material that doesn't meet performance. And it's not just the end use performance, what it sees in the field, but performance, as I mean by meshing with the design and also being manufacturable. So that's really what that plastic material needs to be able to perform. And like I said, I think it all relates back to this not a great understanding of how structure and composition contribute to that performance. So when we look at material selection as part of design and development, new product development, or the entire product life cycle, it's imperative that designers and engineers understand that the fundamental nature of plastics. And I'm going to just kind of quickly go through, and again, we could spend a lot more time talking about each one of these topics, but talk about these things that if you're going to do material selection, and if you're going to design parts, or even if you're going to manufacture parts, I think if you work with plastics, you need to understand these key material considerations we're going to run through right now. Anyway, especially important when you're going to select the material. So understanding that plastics are nonlinear viscoelastic materials. This is, again, a fundamental aspect that plastic materials are viscoelastic. That means that they display both viscous and elastic behavior at the same time. They're also largely nonlinear. No matter what property you're looking at, plastics are nonlinear. Certainly, it's very clear to see this in a tensile stress strain curve, but also no matter what properties we're looking at, we see a lot of nonlinearity within plastic materials. Plastic materials have temperature-dependent properties. That means whether we assess properties, and again, I'm illustrating mechanical properties here, but they can be any types of properties, whether we're displaying, or we're evaluating the material at room temperature, maybe -40, maybe +50 degrees C, those plastic properties are going to be dependent on that temperature. And relative to metals, plastic material properties change over a relatively short temperature swing. It's not at all uncommon to see properties shift dramatically over 10 to 20 degrees C, where for metals, you really got to be talking about 100 degrees C or more before you're going to notice an appreciable change in most of the properties. Plastics have time-dependent properties. That means not only are they dependent on what temperature it is, but how long that product is in service. And I'm not really talking about molecular degradation, like UV or oxidation. I'm really talking about if you place your plastic part under load, the mechanical properties of that part will change over time. Because they're viscoelastic, time, temperature, and is what we're going to see in just a minute, strain rate, are all entangled into each other. That means those plastic properties are dependent on all of those things, and time, temperature, and strain rate all impact the plastic materials in the same way. They're all relatable to each other, again, because they're viscoelastic. So plastic materials have time-dependent properties. And as a continuation of that, if we put our plastic material under continuous tensile stress, that product will eventually fail. Now, maybe in an inordinately long period of time, like 100 years, or it may be something within the life cycle of your product. Could be 5 years, 2 years, a half a year. Again, if you place that part under continuous tensile stress, it will crack eventually. And the third leg of that stool is that plastic materials are strain rate dependent. Okay, so how fast we pull or how fast we load a material matters to what its strength is going to be. That's why plastics are very impact sensitive, and a lot of plastics will fail under impact loading. So temperature dependence, time dependence, strain rate dependence. That means it's kind of where we're going to be looking at when we think about a data sheet. If somebody says, how strong is this material? The only answer that is acceptable is it depends. What does it depend on? It depends on the temperature. It depends on how long it's been under load or is expected to be under load, and what the strain rate is. Okay, so again, when we start to think about data sheets, they present a nice package, a nice number for us, but we need to think about what that number really means. Another material consideration is that plastic materials will change chemically and physically in their environment. The best example here is nylon and water. Nylon absorbs water, and when it does that, its mechanical properties change. As it absorbs more water, its impact properties get better, but its ductility, but its strength, I should say, goes down. So there's a trade-off there: strength versus ductility, dry versus wet. And the same thing can be found with other plastic materials. Nylon and water is just the best example. Plastic materials are susceptible to chemical attack and environmental stress cracking. Plastics are great materials, but if they have an Achilles heel, it's that they don't play well with chemicals. And when you're going to think about material selection, you need to think about what chemicals are going to be present in that environment. Plastic materials are susceptible to weathering. So if we put them outside, they're susceptible to UV degradation and to the rain and to other things that are going on. But principally, we're talking about UV degradation. Again, they can degrade through UV. Again, a number of plastics are somewhat resistant, but others will certainly be degraded. The molding process can impart a significant level of molded and residual stress. And when we think about stress on a plastic part, we have to add both externally applied stresses together with any molded and residual stresses together. That's the total stress state of that plastic material. So when we mold, we're naturally going to get residual stress in our part. Again, the molding condition can affect how much stress we get through that molding process. Weld lines, again, another attribute related more to the molding process, but knit lines, weld lines are going to be formed during the molding process whenever we have two flow fronts that come together, particularly egregious in fiber reinforced materials, and our strength is going to be weakest at that knit line location. When those flow fronts come together, we may not get good entanglement of our plastic materials, and if you didn't know that, plastic materials fail mechanically through disentanglement. So if we don't have good entanglement, good fusion at those knit lines, we're going to have an inherently weak location. Again, how strong is your material? It depends. Plastic materials show anisotropy due to alignment of both the polymer molecules and any fiber reinforcement that's present. So if we're going to get tensile strength off a molded tensile bar, that's the easiest thing in the world to mold. All our molecules, and if we have fiber reinforcement, it's all lined up in the right direction. Is that the way that your plastic part is? No, probably not, unless you're molding tensile bars, which I doubt that you're selling a lot of tensile bars. So on your molded plastic part, think about the strength of that material, the mechanical properties of that material, not necessarily just as what would be, longitudinal to the orientation of flow, but also transverse to that. Plastic materials are also notch sensitive. And so when there's a notch, there's typically stress concentration, which focuses and multiplies any stress on our part. So again, our stress state may be higher than we anticipate it's going to be. Now, I know I went through these relatively rapidly, but it's essential if you're going to be doing material selection that you have a good command of all of these things and how they affect plastic materials, so that then you can say, okay, I'm going to look at my design, I'm going to look at my manufacturing, I'm going to look at my service environment, and now I can start to select a material that's going to weave those three together and not fail. So we talked about those kind of inherent properties. We're going to talk a little bit now about composition, okay? Because that plays an equally important role. Again, if in the material selection process, we have to have an understanding of polymers and additives and their properties. This is going to be an essential to selecting the right material. So we need to know that polymer architecture and how the polymer, the base plastic, the base polymer in our plastic is going to contribute to the overall performance. And then what we do with additives, how that can alter the performance. So when we look at this, and if we were going to spend a lot more time doing this, if we were going to spend days doing this, we would cover all of these things in, I think, what they should be covered in, a lot more time we would spend with these things. We're going to walk through them relatively quickly today, some of the highlights, so that you can understand some of those key things that determine how that plastic material performs. So there are essentially two ways to form a polymer, to undergo polymerization reaction. One is addition polymerization, where we basically are opening up a carbon-carbon double bond. So here we have styrene. We have a carbon-carbon double bond on that. Through the polymerization reaction, we open that up and we form this polystyrene, basically just building blocks onto that polymer. But we start with one monomer, polystyrene. The second general way to do this is going to be condensation polymerization, where we start with two different materials. Here we're making PET, and we start with ethane diol, and we start with terephthalic acid. And what we get is PET out of it. We react this OH functionality with this acid functionality, and that forms a bond, and we build that way. Okay. We also form some water in general that comes off of our molecule. Again, not essential that you understand the depth of polymerization, but the two different ways to polymerize materials means that we get different characteristics. The disadvantage of condensation polymers, where addition polymers have an advantage, is that condensation polymers are more difficult to produce. That means that they have a higher cost, generally higher density, again, which will contribute to higher cost. They're more difficult to process because they typically have a higher melt viscosity, and it's critical that we dry condensation polymers. Otherwise, we can undergo hydrolysis right there in the injection molding machine. All of those things means that they have a higher cost. They typically also have a narrower processing window. And we can't get extremely high molecular weights with condensation polymers as we can with addition polymers. Okay, those are the disadvantages, principally revolving around cost. Advantages are that they give us a wide range of mechanical and thermal properties. This would be the material, if you're thinking about replacing a metal, if you need a high-end performance material, these are what you're going to go to. You're going to go to condensation polymers, okay? And so that typically is the trade-off. Not unexpectedly, cost necessarily versus performance is the trade-off with condensation polymers versus addition polymers. So when we have these building blocks and we put them together, okay, there are a number of ways that relatively similar materials that might be considered to be in the same general family can be different. So here we have polyethylene, here we have polypropylene. The only difference is that one of the hydrogens from polyethylene has been replaced with a methyl group, CH3 group. Because of that relatively small difference, otherwise, the backbone of the polymer is the same. It's just carbon units, just have this small little difference. That means, however, that polypropylene has a higher modulus. It's a stiffer material, has a higher melting point, so it has better thermal properties. Conversely, it's more brittle. It has lower or worse impact properties because it has a higher glass transition temperature. It also has somewhat of a lower crystalline structure. All those changes just because of this. Again, polyolefin materials, polyethylene and polypropylene, just a small little difference. Another way that analogous materials can differ is by what's present on the main chain. So here we have PET, polyethylene terephthalate, with just 2 carbon units there in between basically our ester groups. And we have PBT, polybutylene terephthalate, with 4, okay? But there's a significant difference, even though, again, relatively small change. The PBT is going to have a lower modulus. It's going to be more flexible, but it's also going to have higher impact resistance. It's going to have a lower melting point, so lower thermal properties. and a more crystalline structure compared with PET. It's easier to organize that material into structures. So again, both of these would be thermoplastic polyesters, very similar materials. The same can be true with nylon. We've got nylon 6 or 6.6 or 6.12. Again, melting points are going to be different. Glass transitions are going to be different. Water absorption levels will be different. All the mechanical properties of these materials will be different. Same kind of what's present in the main chain. And then finally, the building blocks and putting them together in different ways. So these are polyaryl ether ketones. So the most common material in this family is going to be PEEK, P-E-E-K, but there are a number of different ways to put ethers and ketones together and benzene rings together. That's really all these are made out of. Different ways we can put them together to get different glass transitions, which is going to determine what temperature that material goes from being very stiff to being much more pliable. Melting point, so high-end temperature performance. That is all based on what we put them together and the ratio of the ketone and the ether functionalities. So again, that small differences within these polyaryl ether ketones makes a big difference in performance. Our next topic I want to talk about, once now we're past polymerization, is going to be branching. This is most prevalent within polyethylene. We've got high density polyethylene, low density polyethylene, and everything in between. Really, the difference between low density polyethylene and high density polyethylene is how many side chains we have coming off. With low density polyethylene, we have large and many side chains coming off. That's why it's called a branched chain, because there's a lot of branches. High density polyethylene has some branches, but they tend to be very small and they tend to be very far and few in between. That means that we can pack more high density polyethylene into space. That's why it's high density, okay? Because we've got less of those side chains kind of getting in the way of packing things nice and neatly. The implications of that are mechanical properties associated with crystallinity, okay? The modulus on high-density polyethylene, the strength on high-density polyethylene, both of those are going to be higher than low-density polyethylene because of that, okay? So particularly when we think about polyethylene, when you think about branching, which relates directly back to density or specific gravity. Another material that this is important for is going to be polyphenylene sulfide. There is linear and branched PPS. And again, that will give you some different performance properties out of it. Not quite as common as polyethylene, certainly, but still a material we need to think about linear or branched polymers. Our next topic is going to be tacticity. And tacticity just means if our molecule is asymmetric, it's not symmetric, say top to bottom. This is polystyrene. Okay, if we draw a line down the backbone of the polymer, what's on the top is not the same as what's on the bottom. For polyethylene, it would be the same. There'd be 4 hydrogens here. But for polystyrene, we have this rather large benzene ring, and that's different. It's not present here on the bottom. So tacticity has to do with the orientation of those repeating units, whether it's up and how it alternates as we progress down the length of the chain. So for atactic polystyrene, which is what we talk about when we talk about crystal styrene or polystyrene in general, okay, that's atactic. Atactic means that there's no organization to this benzene ring. Sometimes it's up, sometimes it's down. It alternates randomly, okay? Because of that, the material's amorphous. It can't form itself into crystals. And so it has no ability to form crystals, and so it's amorphous, has a glass transition of about 100 degrees C. Another material that is commercially available, it's a great material, underutilized, is going to be syndiotactic polystyrene. Syndiotactic polystyrene means that we alternate one benzene ring up, then down, then up, then down, then up. How it's organized on the ring. That's got to do with the catalysts that are used during polymerization process. They can orient that benzene ring, if you will. Because of that orientation, up and down and up and down, alternating like that, the material can form crystals. That means it has a melting point, actually a relatively high melting point, 270 degrees C. Still has that glass transition at 100, but unlike atactic polystyrene, which loses all load-bearing capability because it's amorphous at the glass transition, there's still some crystal structure here, and so there still is some load-bearing capability above 100 degrees, okay? So that tacticity for non-symmetrical molecules, polypropylene, and polystyrene are the two most common, are going to affect how that material behaves. So again, not all polypropylene is the same. Not all polystyrene is the same. So if we were dividing our world of polymeric materials, we would first divide them by thermostats versus thermoplastics. Now we're focusing today on thermoplastic materials. So when we divide that world in half, we're going to talk about amorphous versus semi-crystalline. We just kind of talked about it with polystyrene and how those materials can be different. Let's dive into that a little bit more. Whether a material is semi-crystalline or whether it's amorphous, and if it's semi-crystalline, how crystalline it is got to do with the functional groups that are present that we have from, our building blocks, if you will, from polymerization. It's got to do with the branching. And it's got to do with the tacticity, the things we've talked about already. So that's going to determine whether a material is amorphous or semi-crystalline. With amorphous materials, we have a totally jumbled structure. There's no organization to that structure. There are no crystals, okay? Totally random, totally jumbled. With semi-crystalline materials, we have some crystalline structure. Now, we still have a significant amount of jumbled mass of molecules, amorphous content, but there are some levels of crystallinity, some levels of organization to that material. So an amorphous material, like I said, totally random, totally jumbled structure. Because of that, it only has a glass transition temperature. At that glass transition temperature, all load-bearing properties are going to be lost. That material would become essentially a pile of ooze, okay, at the glass transition. So for polystyrene, about 100 degrees. Polycarbonate, about 150 degrees. Polysulfone, about 225 degrees. Those are the temperatures above that material will lose all load-bearing capability. Does that mean you can use them right up to that temperature? No, because of creep and time dependency that we talked about. But again, that's where that short-term, having some structure to being, like I said, a pile of ooze will come in, okay? Again, because of the structure of materials like PVC, like acrylic resin, like SAN, those materials are unable to form crystalline structure, and so they are amorphous. Some materials, again, are semi-crystalline. We use the word semi-crystalline because there is no such thing as 100% crystalline polymer. So these semi-crystalline materials still have a significant amount of amorphous content. Because of that, they have a glass transition, and their properties will change above that. For example, nylon 6 has a glass transition temperature of about 60 degrees C. So below 60 degrees C, it's going to be relatively stiff, okay? Above 60 degrees C, when we get to that glass transition, now those amorphous molecules can get more movement. That material is going to get considerably more pliable, okay? So that's important to understand that they have glass transitions. But because they have crystalline structure, they also have a melting point, okay? And so materials like polyethylene, polyacetal, nylon resins, PBT can organize themselves into crystals. Okay, this is an important slide. One of the most important slides probably in the presentation today to talk about the differences between semi-crystalline and amorphous materials. Semi-crystalline materials have a distinct and sharp melting point, whereby amorphous materials soften over a relatively wider range as they go through glass transition. Semi-crystalline materials are going to be opaque or translucent because the crystals interfere with the ability of the light to get through the material. Amorphous materials are transparent. Semi-crystalline materials give you better organic chemical resistance because of that crystalline structure keeps the chemicals out of the molecular path or, out of the structure of the polymers. Amorphous materials lower organic chemical resistance. Semi-crystalline materials tend to give you higher strength, higher stiffness. So higher tensile strength, higher modulus materials. You get better ductility out of amorphous materials, okay? You get better fatigue and creep resistance, as a general rule of thumb, out of semi-crystalline materials, but you get better toughness, better impact resistance out of amorphous materials. Lower density for amorphous materials, higher density for semi-crystalline materials because you can pack more. They can get those molecules together more, and accordingly, higher mold shrinkage for semi-crystalline materials. Molecular weight, another very important aspect of polymeric materials. When we talk about properties and we talk about selecting a plastic material, there's going to be a range of molecular weights to use. Most oftentimes that's on a data sheet represented by melt flow rate, which is not necessarily an all-encompassing look at the molecular weight. It's a snapshot of the average molecular weight of the material for comparison purposes, okay? So when we select a higher molecular weight material, a lower melt flow rate material, when we select that higher molecular weight material, our tensile strength is going to be better. At the same time, our elongation at break is going to be better. So strength and ductility moving in the same direction. That hardly ever happens, but it happens when you select a higher molecular weight resin. We get better yield strength, better toughness, better hardness, abrasion resistance, better softening temperature, and very importantly, that higher molecular weight material will give us better chemical resistance. All of this comes because we have a better level of entanglement in a higher molecular weight material. We have longer chains that can entangle into each other. And here's just some data sheet examples to show us that. Here we have polycarbonate. And when we choose polycarbonate, we have a wide range of MFRs to choose from. So 7 is of these 3 is our high molecular weight material, 17.5, our low molecular weight material. And we see that our impact resistance and our strain at break are all better with our higher molecular weight material. Here's some polyacetal. Fatigue resistance is better with our high molecular weight resin. Environmental stress crack resistance of this high density polyethylene, again, better when we have higher molecular weight resins. So when we think about polymeric materials, we can either have homopolymers or copolymers. Homopolymers simply have the same building block, repeat unit, over and over and over again. Copolymers have 2 or more building blocks that are put together during the polymerization phase that can alter how that material behaves. So copolymerization is very common to kind of tweak our material properties. In fact, this is one of the areas that resin suppliers are working on very diligently to create new resins by copolymerization. So, for example, polypropylene is copolymerized with ethylene. When we do that, that copolymer gives us better impact resistance, better low temperature properties. At the trade-off, because polypropylene homopolymer is going to be stiffer and stronger. Again, there's a trade-off. There's a compromise, if you will. Polyacetal copolymers have better oxidative stability compared to the homopolymer, better impact properties, but again, at the expense of strength and stiffness. So there's always a plus and a minus. So when you're looking at copolymers, you need to think, okay, what am I giving up for what I'm getting? One of the best examples of a copolymer, and this is actually a terpolymer because it's a 3-function system, is ABS, acrylonitrile, butadiene, and styrene. Each one of them brings something different to the table. And with ABS, you can have almost an unlimited number of different grades of ABS because you could have something right in the middle, you could have something out here, something in this corner, something over here. Again, lots of different ways to put acrylonitrile, butadiene, and styrene together to get a material. So the point I want to make here is that certainly not all ABS is the same. It depends on the relative levels of acrylonitrile, butadiene, and styrene, and that will certainly have an effect on performance. Kind of the twin sister, if you will, of copolymerization is blends and alloys. Copolymerization is done during the polymerization stage. Blends and alloys are just that. You take 2 polymers or more and you blend them together mechanically. Not something you're going to do at the injection molding press, but something that is done under very exacting conditions by a compounder. And again, much like copolymerization, you do that in order to get the properties, tweak the properties that you want. This is another area that resin suppliers are working on to create new resins, okay? And there's a lot of different blends and alloys that are available. And this is just a small list. There are hundreds and hundreds of different types of blends or alloys that are out there. So why might we want to do that? Well, say we're making a medical device. And when we do a handheld medical device, and when we do that, we have a choice. One of the materials we can use could be polycarbonate. Great impact resistance, good dimensional stability, good heat resistance. Why does it have those? Well, because it is an amorphous resin. What's the trade-off with amorphous resins? Well, they tend not to give us great chemical resistance. And in fact, polycarbonate, if it barely looks at an organic chemical, it's going to undergo environmental stress cracking. So that may not be the best choice. Another material that we might be able to make this device out of is going to be PBT. Okay, great chemical resistance because it's semi-crystalline, high strength, high stiffness, good flowability. Because it's semi-crystalline, what's its weakness? Well, impact resistance. If we drop this, it might break. So what kind of resin might we use? Well, a very common blend is going to be polycarbonate PBT. This is a material that's used in a lot of different applications. Does that PBT have all of the impact resistance of polycarbonate? No, it doesn't. Does it have all the chemical resistance of PBT? No. But that blend brings some of both to the table, and that we might have a resin that's suitable for our application that gives us some impact resistance and some chemical resistance. Again, a lot of different things to think about with blends and alloys. Again, it's a little bit like a trade-off. So additives, we could spend a week talking about additives, but just understand that when you put an additive in, it's going to change a property that you're trying to modify. You can add flame retardants, which will change how quickly the fire spreads or what it does when it starts on fire. But as I walk through these, and I'm not going to mention it for all of them, there are always trade-offs, okay? You get the flame retardancy, but is it also doing something else to the property? Many flame retardants make a material more brittle, okay? So they make that material, so it's not going to have an elongation to break or an impact resistance with a non-flame retardant grade, okay? So that's something you want to be cognizant of is what's my trade-off for adding this? So flame retardants, probably the most common additive used in plastic materials is going to be anti-degradants and stabilizers. Just about every grade. In fact, I think every grade of plastic sold has some level of antioxidant, so it can withstand the injection molding process. And so you can have antioxidants, antiozonants, UV stabilizers, hydrolysis-resistant additives. There are additives to prevent most types of degradation. Again, you have to think about what your application is. What is the best looking package in order to be able to stabilize that material? How much do you need? Colorants. Plastic materials are great because they offer the ability to have these aesthetic properties that we don't really get without having to paint. Okay, and you can't do that with for color, fluorescence, a lot of different things. You can modify that performance. Again, you need to be thinking about in mind, but my properties. For example, blue pigment added to a semi-crystalline material tends to make that material more crystalline and tends to make that material a little bit more brittle. Plasticizers are materials that make the material more soft and pliable. It's the difference between PVC pipe, which is hard and rigid, and PVC electrical cord, which is soft and flexible. Again, we can add some of that. Fillers and reinforcers, very, very common material, probably second after stabilizers that are found. Again, they can help to adjust mechanical properties, physical properties, and also in many cases take cost out of the overall resin. Okay. Be aware that there are two different types. Reinforcing fillers. These improve the mechanical properties. These are fibers, high aspect ratio minerals, so like glass fibers, carbon fibers. Okay, they're going to build strength. They're going to build stiffness into our material. Then there's non-reinforcing fillers. They basically add bulk and they help to take cost out. Things like glass beads, kaolin clay, talc, calcium carbonate. They're going to maybe add a little bit of stiffness. They can actually bring the strength down. So they won't add strength, but they will take some cost out of the material. Nucleating agents and clarifiers make that, kind of change the appearance of the material. And then finally, a whole host of specialty additives, a lot of different things that we can add to that material. Okay, so I'm done with that first part. We talked about those essential material characteristics. We talked about the composition of the material. Let's get on now to the actual material selection, okay? And I'm going to start by saying that there is no defined absolute recipe. If you came here thinking that I'd be able to, say, do this, do this, boom, you come up with the right resin, that's not really the case. There is no absolute recipe. There's no playbook for material selection. It truly is half art, half science. There's a lot of experience that goes into it. And there's, again, looking for the science behind it. So step one, where you always want to start, I said there was no absolute, but I think this is an absolute. Where you want to start? You want to define the requirements of the application, not just the service application, the requirements of the service, but also because of my design, what are the requirements of this material? If I have sharp corners, well, I certainly maybe want to stay away from a material that is not sensitive, right? Processing, okay? How am I going to process this material? And what does that do for my material selection? How do I assemble it or install it? How does that impact material selection? So you want to think, and then finally service. What is it going to see? Temperature-wise, mechanical property requirements, weathering, things like that. All of those kind of things that once we put that product in the field, what's it going to see? We need to think about all of those as we start to define the requirements of the application. Successful material selection depends on an early and accurate assessment of the application requirements. What do I need this material to do? And then somehow we also then need to tie those in with property data that's available. So as we start to define requirements, our first question is going to be why? Why am I undergoing material selection? Have I had a failure and something went wrong? Am I looking to take cost out of my product? Am I coming up with a brand new product and I want some cool features in it? Okay. And there's a lot more, but the why really does affect how I select material and what materials I might go towards. Again, if I'm trying to take cost out of this product, well, certainly I need to be aware of what my application requirements are, but I'm also going to be gravitating towards maybe lower cost material. So the why is very, very important, and you need to understand that. Then we're going to look at aesthetics and appearance. Again, does this part need to be clear? Well, if it does, probably going to have to be with an amorphous-based material. Does it need to be super glossy? What do I need this product to look like? What are my physical properties? In terms of strength and stiffness, things like that. Electrical properties, all of the physical properties that I need that part to withstand. Environmental exposure. Is this going to be used outside? Is it going to be used under fluorescent lights? Is it going to be underwater? Okay. Where is this product going to be used? Regulatory issues. Is this something that needs to comply with FDA? Is it what type of regulation is out? And there's only more and more regulation that seems to be happening. So again, you have to be aware of that. How am I going to manufacture and assemble this? Okay. Is it a tank that I want to blow mold? Well, that's going to, maybe move towards certain molecular weight resins and things like that. Am I going to extrude this? You need to satisfy all these in order to be successful. But I don't live in an ivory tower, so I understand that cost is an important aspect of that overall product. Okay. But I am going to say this. This is my example. I have a snowblower, and $600 snowblower. When that 50-cent plastic part breaks and I can't use my snowblower, okay, I get very upset. As a consumer, I would gladly have paid an extra 50 cents to pick the right material so that $600 product doesn't fail. Again, that's kind of my example that I think about. How important is cost? What else beside this plastic part is all coming together to form, what the consumer is going to get? So anyway, cost is important. So short-term properties, these are the things that we use most often when we think about material selection. Tensile and flexural properties, strength, modulus, elongation, yield, impact resistance, heat deflection, temperature, and softening point. These are the things that we think about most often. But these are the things that we really should be thinking about. Creep, so creep rupture, static stress over time. Stress relaxation, which is static strain over time. How is that material going to relax over time? So creep, how much is it going to stress and might it crack? Stress relaxation, how much am I going to, again, lose fit, things like that. Fatigue, dynamic stress over time. Heat resistance, both degradation and warpage. Chemical resistance, degradation and environmental stress cracking. Weathering resistance, UV, pollution, rain, humidity. And this is not by any means an all-encompassing list of long-term properties. It's the ones that I see most often. But we need to be thinking about long-term properties, and we also need to understand that they cannot be predicted from short-term properties, okay? For example, because of if we're comparing two materials and one has a higher tensile strength, that does not mean it's going to have a better fatigue resistance than the other material, okay? In metals, sometimes you can make that jump. In plastics, absolutely cannot make that leap, okay? Long-term properties, those things important for our application, can generally not be predicted from short-term properties, okay? So we have our application requirements. In order to avoid failure, we need to be able to match them to some property data. This leads to data sheets. This is, one of the things we go to, right? We pull a data sheet and we're going to start searching, what are the properties of this material? Property data sheets have essentially remained unchanged over the last 40 to 50 to 60 years. They're almost like they're an industry standard. But, back in the 60s and 70s, we were making things like this Viewmaster. I had one of those. I'm old enough to have had one of those. Again, toys. That's what we were making. Now we're making high-end aerospace parts, demanding medical applications. But yet the data that we make material selection decisions on doesn't seem to have changed over 40, 50, or 60 years, okay? What do we get on data sheets? Well, we get tensile strength at yield, usually at room temperature, elongation at yield or break, again, room temperature, modulus, room temperature, heat deflection temperature, which is a totally useless property. If I had more time, I'd go into that, and I'll give you my email address at the end. If you want to talk about that and understand why I think that that's a bad property, I'd be more than happy to talk to you about that. Notched IZOD or Sharpie, which is a pendulum test, again, not the best impact test for plastics. Coefficient of linear thermal expansion, usually at one temperature, and electrical resistivities. These are commonly found on data sheets, but do they tell us anything? They're usually giving us mechanical properties at some catastrophic point. Do we care about that? Well, unless we're making little rings that milk jugs, are used to, when you break them open, what do you really care about the break strength of the material? You're not operating at break, hopefully. You're not operating anywhere near break, okay? So not advocating we get rid of that property, but we need to talk about some other properties that fill in lower stresses and how that material behaves at lower stresses. What else do we get on data sheets? Well, we get, impact resistance, strength stiffness, almost exclusively at room temperature. Where's your product used? Yeah, many of our products are used at room temperature, but a lot of them are used outside. In the summer, it's very hot, or in the winter where it's very cold, okay? So we need properties across the temperature range. We get thermal properties like HDT, essentially defining the failure near the melting or the softening point of the material. Again, how does that help us? I'm not sure how that really helps us. And remembering that all of the numbers we get on a data sheet are points on a curve, but we're not getting the full curve. That would be helpful, okay? Remember, as we talked about earlier, plastic material properties change with temperature. They change with time. They're nonlinear, and they're influenced by the conditions in which we expose that product to. So better decisions are made when we get better graphical-based data rather than tabular data, okay? So what do we need? I'd like to see stress strain curves at various temperatures, and not just numerical values, but the actual curve, and not just the curve, but the actual Excel sheet to produce the curve. Okay, I'd like to see modulus versus temperature, like a DMA curve. I'd like to see coefficient of expansion versus temperature, how that changes. Instrumented impact testing, multi-axial impact testing data. Thermal properties with temperature. Isochronous stress strain curves, like you would look at for creep data. I want to see fatigue data. I want to see viscosity versus shear rate data to help me with molding. These are the kind of things that I want to see, and the only way to get them is to demand them from our resin suppliers. When you're thinking about using a resin, ask for this type of data. And in fact, if you can, say, I need this data, or I'm just not even going to consider your resin, okay? I think that that's a reasonable statement. So again, back to kind of where we started before I jumped on my soapbox. We need to define all of the requirements for that material, okay? So there's a lot of them. Again, checking boxes off, looking at whatever needs to be, required from our material to be successful. Step 2 then, that was all step 1, defining those requirements. Step 2 is going to be conduct an initial survey to look at potential candidate materials, polymer families. So we're going to review candidate families for strengths and weaknesses. We're going to look for maybe similar products that are used out in the field. What general families are they using at? We're going to look at, are there new material developments that offer us some new opportunities? Again, looking at all of these things, okay, all of these things, really excluding the additives, all of these things to look at which family of plastic, am I going to use? And there's a lot of different families, okay? So we want to look at all of them. So then you basically pass all of these through what I consider kind of looks like a filter. All of our, why and aesthetics and performance, the performance properties, environmental exposure, regulatory, all of that. And some materials will drop out along the way. And what you get out at the end are materials that are potentially suitable for your application. Okay. Again, start with all the materials. Start with basically this whole list. Okay. And then filter them out. Step 3 is going to be to look at additives. For example, if I need some very stringent flame retardant properties, or if I need something to last a long time at relatively high temperature, I might need a different antioxidant package. So you start to look at additives that might be required specific to your application. Then review the design to look at how these part features are going to affect material selection. And then again, balance that again. So material selection, product design, and manufacturing aren't something that you throw over the cube at somebody and now it's your turn. They're all done kind of together, iteratively, but together, okay? And so you want to look at things like the wall thickness, the corner radii, the ribs, the assembly details, all of those things in order to say what unique characteristics does that mean for my material. Then we're going to look at costs, okay? And cost means we're going to look at the entirety, including not just the per pound cost of the resin, but all of the manufacturing costs that go into it, okay? And so how much is this part going to be when I look at it, okay? And again, considering, as I said, when you think about cost, what am I putting this plastic part into? A lot of metal, a lot of expensive materials that when this plastic part fails, the whole thing fails. That's got to be a factor in cost, I believe also. Then you want to conduct a process and performance simulation. So performance simulation would be FEA. We want to use FEA, and we'd like to use properties unique to the specific materials that we're considering at this point. So not just generally polycarbonate, but if we're thinking about Lexan 101, what are the FEA performance properties for Lexan 101? The same thing on the process side. We want to do a mold flow. We want to look at that, see how this material is going to mold. Because is it moldable? Is this the right material that way? Is the molecular weight too high so that my melt viscosity is going to be very, very high and I can't get it to fill the tool? Again, got to go hand in hand. So use the specified material, do those things and see, do I look like I still have the right material? Then actual comparative testing based on product requirements. Again, we're still at the material stage at this point. Chemical compatibility testing, creep, impact, UV, whatever is unique or important, I should say, to your application. Okay, that's the kind of testing that you want to do. Finally, some keys to success. Again, understand what the part will experience in the field. You have to do that. Keep all the costs in mind. Find the right material property data, both single and multi-point. Determine what tests need to be performed if you can't get all the data you need, how to perform it, what the right way to go there is. Make sure that you do the right computer modeling, mold filling simulations, finite element analysis. Use past experience. Like I said, it's an art and a science together. What's worked in the past? What hasn't worked? Failure is a powerful tool for material selection. Again, understanding why and how something has failed will help you to select a material to avoid that failure in the future. Have a good relationship with the material supplier. Again, don't always beat them up about cost. Understand that they're providing you something very, very technical, and there may be a cost for that. Also, have a good relationship with your molder. They're an excellent source for material information. And in the end, accept that you may end up with a non-polymeric material. You may end up with a metal. We've all seen charts like this, pyramids or triangles, where we've got kind of a hierarchy of materials. I just want to spend a minute saying there are no such thing as commodity polymeric materials. That term absolutely aggravates me because when we talk about commodity, we talk about interchangeable. And we simply know that, different grades of polypropylene, polyethylene, ABS, whatever you consider a commodity material, they're not interchangeable. One grade of polypropylene is not going to perform the same way as another. So again, don't get that mindset where we think about commodity materials. Don't think about hierarchy. Think about what properties do I need to satisfy and which material is the right way to do that. Just a little plug here. If you thought that this was interesting, the Madison Group is putting on a 2.5-day material selection course. And you can get that information here. Also, you'll see my email address at the end on the next slide. If you don't get that scanned or whatever, that's fine. You can reach out and contact me. Again, 2.5 days about material selection. If you thought that this was interesting and it kind of piqued your interest, we're going to really dive into things there. At this point, I want to say thank you to Sodick, and also I'll take any questions. I know I went a little longer than I thought. I apologize for that.
All right. Well, thanks, Jeff. That was really informative. I appreciate you sharing your knowledge with us, and we're definitely looking forward to having you here for that seminar that you're going to be given.
Yep. Oh, yeah. I forgot to mention, it's going to be right there at Sodick. So, yeah.
Yeah. Yeah, you're going to be right in our facility, and we're happy to have you. We do have a couple of questions coming in. Again, if you guys have questions, submit them into the Q&A tab. And I'll go ahead and get started here with some of the questions. The first one I'll take, it says, will we receive a copy of the slides? I would say that you can reach out to Jeff if there's anything specifically that you want to see, but we will also be posting this webinar to our YouTube page, so you can revisit it there as well. I'll get to the next one here. It's considering branching and cross-linking, how close can we get in practice to an isotropic material with plastic? I imagine if you made something like this, creep would eventually degrade the randomness. Is this accurate?
Yeah, I mean, with branching, certainly branching, as I'm thinking about polyethylene specifically, branching interferes with crystalline structure, and the more crystalline the material is going to be, generally the more creep resistant it's going to be. So high density polyethylene is more creep resistant than low density polyethylene. So the more you get branched, the less ability that material has to form those crystals. Now you might think the more branched it is, the more entangled it would be. But that's not necessarily, that may be the case. You might get some additional entanglement, but the lack of crystallinity, the lower crystallinity really predominates there. So if you're talking about, polyethylene, that's the case. I know that PPS, there is some talk of cross-linked PPS. It's not really cross-linked. It's just a branched version of PPS where those branches kind of simulate some cross-link structure, but it's not truly cross-linking. If you want to talk about that a little bit more, feel free to reach out.
Awesome. Thank you. Here's another one. What is the best way to detect molded in stress that would trigger a failure? Can you share this presentation with the group?
Sure. So molded in residual stress, there's a couple different ways to do that. Certainly you can estimate molded in residual stress through mold flow simulation, and that's a good place to start in many cases. Otherwise, molded in residual stress can be, in a clear material, can be evaluated using polarized light. And you can either do that qualitatively, or there's actually an instrument in clear materials to do it quantitatively. Or thirdly, for amorphous materials, a number of materials like polycarbonate have kind of set chemical resistance tables. And by that, I mean, there's a process where you would submerge a polycarbonate part into a solvent system. You look for cracking, and the time it takes to crack then directly relates with a correlation curve to the amount of molded and residual stress in buckets, like 400 to 600, 600 to 800, 800 to 1,000. So you get close. So there are a number of different ways that you can approach molded and residual stress.
Thank you. Thank you. Another one here. How do you approach material substitution?
Sure. So material substitution, and this was quite common. We got this question a lot a few years ago when there seemed to be some shortages. I like to do that up front, anticipating that at some point in the future there might be a problem. So you've gone through the work of qualifying material A. Hopefully you've put it on your part drawing. This is the material we're going to use. What we don't want to see on the drawing is, I want to use a 30% glass fiber reinforced nylon 6/6, okay? Because there's a lot of different materials that satisfy that. So I like to see the resin right on the drawing. After you've gone through the pains of doing that, while you have time, qualify a second and third resin, putting it through some of the same testing, that key testing, and getting it qualified, putting it on the drawing that that they're in, that can also be used to give your molder some cost, so some ways to reduce cost. But again, I want to see that material being qualified in the same way we qualified the original material.
Okay, well, thank you. That was interesting. Another one here. What kind of validation testing is required to feel confident in a material?
Sure. So really the validation testing, the material testing is going to depend on the application. I don't want to, throw the kitchen sink at the, in terms of testing at a material. I'm going to pick the tests that are going to be most important. For example, if it's going to be outside, I'm going to want to do some UV testing. If it's subject to fatigue loading, maybe some fatigue testing would be important. Chemical resistance testing, again, if it's contact with certain chemicals or cleaning agents or things like that. So pick those tests that are, or those factors that are most important for the success of the application and test against those.
Great, thank you. We're getting close to the hour here, so I'm just going to have one more for you,
Sure.
and then we'll wrap it up. Can you please revisit again how the why is so important?
Sure. So why is important because it kind of determines, what do you want to get out of this material selection? What are you hoping to get? What are you hoping to avoid? If you're solving a failure, basically you've had field failures and you determine through a failure analysis that it's because of you didn't have the right material. Well, then we know how it failed. Creep or fatigue or impact or whatever the failure mode was. Well, now we want to get a material that's better for that particular type of thing. So that's on a failure. Again, if we're taking cost out, well, then I want to gravitate towards a lower cost material as long as it still satisfies my requirements. So the why is really important because it sets the stage for where am I headed with this material selection.
Great. Well, thank you. We're going to go ahead and wrap it up. I think Len might want to say hi to everyone as well. Len, are you there?
Yeah. Yes. Can you hear me okay?
Yes.
Jeffrey, thank you so much. That was just fantastic information. I urge everybody here. This is one of the most well-attended webinars that we've had, and we've had probably over 60 of them. So please reach out to the Madison Group and Jeffrey. They've got a unbelievable team. We're very lucky to be able to partner with folks like this. And thank you all for taking time out and attending our webinar. Much appreciated.
Well, thanks, Len. And I second that. Thank you, Jeff. That was very informative. And thank you for sharing your knowledge with us. And we look forward to seeing you here in a couple of months.
I look forward to being there. Thank you.
Yeah, great. Thank you. Bye now.
Thank you.
Bye.